Welcome to Critical Thinking Deductive Arguments. In this first part, we're going to be looking at an introduction to the general concept of deduction or deductive arguments. This presentation is based on the textbook, A Workbook for Arguments by David R. Morrow and Anthony Weston, but contains some additional commentary, interpretation, and concepts. So let's begin by looking at what a logical argument is. An argument is one or more propositions given as proof of or evidence for another proposition. A proposition is a sentence or a part of a sentence that is either true or false. It has a truth value. Now, not all sentences or parts of sentences or other utterances are things with truth values, but propositions are. You could think of them as attempts to describe or represent the world a certain way. So if they're true, they represent the world accurately. If they're false, they don't represent the world accurately. There are actually other interpretations of what truth means, but that's a kind of intuitive way of understanding truth, at least for the purpose of defining a proposition. Now, the propositions in an argument are going to be of two kinds, premises and conclusion. Every argument has exactly one main conclusion. That's the proposition that the argument is trying to prove. And every argument has one or more premises. The premises together are given as evidence for or proof of the conclusion. An example of an argument is all men are mortal. Socrates is a man, therefore Socrates is mortal. In this case, lines 1 and 2 are the premises, and line 3 is the conclusion. The word therefore serves as an indicator of the conclusion of an argument. There can be other indicator words as well, such as thus or so. So let's look at the different kinds of logical arguments that there are. We can divide arguments in many different ways. This way is based on the concepts of validity and strength. So with all logical arguments, these are arguments that are attempting to prove some proposition. They're either invalid or valid. We're using the word valid here in a technical sense. Valid means that if the premises of the argument are true, then the conclusion must be true, logically speaking. An invalid argument is just one that's not valid. So when we look at deductive arguments, we're looking at arguments that attempt to be deductively valid. Among the invalid arguments, though, not all of these are bad or problematic. Some are what is known as weak, others are strong. A weak argument is one in which if the premises are true, it does not logically follow from that the conclusion is probably true. However, in a strong argument, it's probably true that if the premises are true, then the conclusion is true. So the premises don't guarantee the truth of the conclusion, but they make it highly probable. There are at least two main types of strong arguments. You can basically classify them based on what their premises are about in part. So the word inductive can either be used to refer to all arguments that attempt to be strong or a subset, as we're doing here. Inductively strong arguments are ones where you're trying to prove a generalization based on examples. That's a common way of using the term inductive to refer to an inductive generalization. And if you think about it, even if you have a lot of examples to prove a generalization, there's no absolute guarantee the generalization is true. It's a matter of probability. And abductively strong arguments are ones in which you're trying to show the conclusion is probably true based on the premises, but the conclusion is something about causation. You're trying to prove that some thing is the cause of or the explanation for another thing. With regards to the textbook, A Workbook for Arguments, inductively strong arguments relate to Chapter 2 on generalizations, and abductively strong arguments relate to Chapter 5, arguments about causation. So let's look at the concept of deductive argument. This is what this part of the critical thinking textbook, Chapter 6, is about. A deductive argument can be defined as one that purports or attempts to be valid. That is, it's not necessarily one that is actually valid, but that's its goal or intention. And yes, this does require an active interpretation to figure out if an argument is even trying to be valid in the first place. But if it is, then it counts as deductive. Deductive arguments can be either valid or invalid, but what makes them deductive is that they're attempting to be valid. By the way, Sherlock Holmes is often described as a master of deduction. So on the one hand, you could use the character of Sherlock Holmes to help remind you of what deduction is. It's a type of reasoning or a type of argumentation. However, if you look at most of the reasoning he does, or much of it, it's actually what we would call examples of abduction, or where you're trying to reason at the cause or the explanation of some phenomenon. Generally, in the case of a mystery, a whodunit, or a crime you're trying to solve, you're looking for an explanation of the crime that includes a perpetrator, a motive, etc. So this is actually reasoning abductively for the most part. Let's return to this concept of valid or validity. A valid argument is one in which it's logically necessary that if all the premises are true, then the conclusion is true. And you'll notice this is kind of an intuitive concept. If the premises are true, then the conclusion is true, as a matter of logical necessity. However, I've capitalized the word if because the definition is a hypothetical definition. It's not saying that the premises are true. It's saying if the premises are true, then the conclusion is true. So the example of an argument I gave earlier is an example of a valid argument. If it's true that all men are mortal, and if it's true that Socrates is a man, then it would also have to be true that Socrates is mortal. So before we move on, let's look at some questions about validity. Can a valid argument have a false premise? Or can a valid argument have a false conclusion? Think about these questions using the definition of valid from the previous slide. The answer is yes. Actually, it's possible for a valid argument to have both a false premise and a false conclusion. So here's an example. All cats are dogs. Socrates is a cat, therefore Socrates is a dog. What makes this argument valid is that if the premises were true, then the conclusion would have to be true. So that comes back to the hypothetical definition of valid. The word if appears in the definition. It's not saying that the premises of a valid argument are true. What makes the argument valid is that if it turns out the premises are true, then it would also have to be the case that the conclusion is true. So validity is sometimes described as truth preserving. When you put true premises into a valid argument, then the truth of those premises is preserved in the conclusion. The conclusion would also be true. If you look at this example, it has at least one false premise. All cats are dogs. And that's the only way an argument that's valid can have a false conclusion. If you know an argument is valid, but you also know the conclusion is false, then you also know that at least one of its premises is false. Because otherwise, if it's valid, the conclusion would have to be true. In this case, suppose it is true that this cat is named Socrates. Even though that premise is true, because premise 1 is false, that makes it possible for the conclusion to also be false. Invalid just means not valid. In an invalid argument, it's logically possible for the conclusion to be false, even if all the premises are true. So an invalid argument is not truth preserving. If it's invalid, the conclusion can be false even if the premises are true. So here's an example of an invalid argument. All men are mortal. Socrates is mortal. Therefore, Socrates is a man. This is very similar to the valid argument we looked at before, but there's one subtle difference. The second premise does not say that Socrates is a man. It says that Socrates is mortal. And that one difference is enough to make it invalid. We can illustrate its invalidity with an example. Suppose Socrates is a mortal creature but is not a man. Perhaps Socrates is a dog. Then, even though the premises are true, all men are mortal, and Socrates too is mortal, Socrates the dog is mortal, but it does not follow that Socrates is a man. In this case, he's actually a dog. However, even if we were talking about the human Socrates, the argument would still be invalid because of its logical form. Even if the premises are true, those premises don't prove the conclusion is true. That's what makes it invalid. So let's look at some questions about invalidity. Can an invalid argument have a true premise? Can an invalid argument have a true conclusion? Think carefully about the definition of invalid. The answer is yes. It is possible for an invalid argument to have both a true premise and a true conclusion. So let's go back to that same argument. All men are mortal. Socrates is mortal, therefore Socrates is a man. Suppose in this case we are talking about the human Socrates. Both premises are true. The conclusion is even true. So what's the problem? The problem is that those premises do not give you reason to prove the conclusion true. The conclusion, if it's true, is true for some reason other than those premises. So there's a logical gap between the premises and conclusion. So that's why it's an invalid argument. Don't confuse invalidity with having false premises. Don't confuse validity with having true premises. They're both defined hypothetically. So in an invalid argument, it's possible for the conclusion to be false even if the premises are true. But that possibility, based on the condition that the premises are true, that possibility doesn't tell you for certain whether the premises and conclusion of the invalid argument are actually true. It's a separate question. So I've mentioned briefly this concept of logical form. When defining whether an argument is valid or invalid, that determination is based on the general logical structure of the argument. It's not based on what the particular propositions in the argument are about. So here's an example of logical structure. Let's take the argument, if it's an apple, then it's beautiful. If it's beautiful, then it's cool. Therefore, if it's an apple, then it's cool. This turns out to be a valid argument. When we make that determination, it's going to tell us something not just about this argument, but about all arguments that share the same logical form or structure. Now, the textbook, A Workbook for Arguments, does not give that much logical notation, but it does give you a way of symbolizing propositions by capital letters. And that's what we've done here. The capital letter A symbolizes the proposition, it is an apple. The capital letter B symbolizes the proposition, it is beautiful. And the capital letter C symbolizes the proposition, it is cool. However, we can abstract away from those particular propositions and just look at the form of this argument. If we know that that particular example is valid, then all arguments that share that same general form will be valid too. So we can think of it as turning A, B, and C into variables, not just abbreviations, but variables. The A, B, and C could stand for any proposition. So another example of this, if it's a human, then it's mortal. If it's mortal, then it does not live forever. Therefore, if it's human, then it does not live forever. It's the same general logical structure, and it's valid. So as a kind of side note, there are an unlimited number of argument forms, both valid and invalid. However, the most commonly used ones are named and classified. And so in this section on deductive arguments, we're going to be looking at some of the different types of valid and invalid deductive arguments. Let's go back to this concept of proposition. A proposition can be defined a bit more carefully as any utterance that is either true or false. Now, initially I defined it in terms of sentences, but technically speaking, a proposition can be part of a grammatical sentence. So a proposition can be just a clause, one clause of a sentence. Sometimes it's also possible, this is more unusual, but it's possible for a proposition to be divided among multiple sentences. So let's give an example of a proposition. It's really any utterance that's true or false. Now, this does not mean that it has to have an indeterminate truth value, like you don't know whether it's true or false. A proposition can be true, it could be false, it could be unknown or indeterminate, but as long as it's the sort of thing that is capable of being true or capable of being false, then it counts as a proposition. So, for example, Spock is a Vulcan. That is a proposition because it's either true or false. The sky is blue. The sky is yellow. All of those things are propositions. So you might be thinking, okay, doesn't every utterance count as a proposition? The answer is no. There are other uses of language other than to try to express the truth of the world or represent the world. So an example of a non-proposition would be a question. Think about that question itself. What is an example of a non-proposition? Is that true? No. Is it false? No. It's not the sort of thing that can be either true or false. Neither one of them makes sense. It's a different way of using language. It's basically requesting information. So a question is not asserting some fact or some truth about the world. It's a request for information. And there are other uses of language as well that are not propositions. Now let's look at the difference between simple and compound propositions. A simple proposition is one that we will symbolize with a single capital letter. It's a proposition that does not contain propositions or logical operators as components. So for example, logic is fun. I'm a monkey's uncle. That's a complete attempt to represent some state of affairs. We cannot analyze it any further in terms of grouping together or connecting in some way other simple propositions. A compound proposition is one that contains at least one simple proposition and at least one logical operator as components. An example of a logical operator is the word or. Another example is the word and. So an example of a compound proposition is either logic is fun or I'm a monkey's uncle. In this case, we have two simple propositions, L and M, but we have a logical operator as well, or. And the compound proposition will at least contain one of those operators. It may also contain, and usually does, more than one simple proposition as well. Let's look at the concept of logical operator more carefully. A logical operator is something that operates truth functionally on propositions. What this means is that a compound proposition with the logical operator, to determine the truth value of that proposition, you can look at it as a function of the truth values of its individual component propositions and its logical operators. Here's a more concrete example of that. Take the compound proposition L and M. An example of this is Trump and Biden ran for president in 2020. This uses the logical operator and, which is called a conjunction in logic. And if we want to know the truth of this compound proposition, we can calculate it if we know the truth of its individual components and the meaning of the and operator. The meaning of the and operator can be defined as follows. The L and M proposition is false if either L is false, or if M is false, or if they're both false. Otherwise, the and proposition is true. So you could think of the logical operator and as being a kind of function over the truth values of its individual components. It operates on the truth value of L and M, which creates a truth value for the whole compound proposition. So here are some of the main types of compound propositions. So note that the capital letters P and Q are standing for simple propositions. The negation is usually represented by the English word not, and we can symbolize it by a tilde. The textbook, A Workbook for Arguments, does not include these logical symbols, but they're included in many logic textbooks. Because it's a critical thinking textbook, it doesn't give you that notation. However, I will be using that notation in some of these slides because it is a convenient way of representing the structure of a proposition and thus the structure of a deductive argument. So not P, the negation, can be symbolized by a tilde. The conjunction most commonly is expressed in English by the word and that can be symbolized by a dot between two simple propositions or two other propositions. The operators can operate either on simple propositions or on compound propositions as components. The disjunction corresponds to the English word or. That's the most common way of expressing the logical idea of disjunction in English. It can be symbolized by that wedge symbol between the P and the Q, P wedge Q. The conditional is an if-then proposition, and it can be symbolized by the horseshoe. So an example of a compound proposition, if an animal is a dog, then it has a tail. In this case, the capital letter D stands for the simple proposition an animal is a dog. The capital letter T stands for the simple proposition it has a tail. And we're symbolizing the if-then via the horseshoe. So before we move on, let's talk a bit more about a logical disjunction. So there's actually two different types of disjunctions. The English word or can be used in either of these senses. In logic, we really value precision. So to remove ambiguity, we have to choose one of these. And most systems of logic define the or inclusively. The inclusive or is a use of the word or in which either or both of the disjuncts can be true. Either or both of the propositions linked by the or can be true. The exclusive or is one in which at most one of them can be true. So you're saying that one and only one of those two disjuncts is true, the other is false. The exclusive or is very common. So here's an example. Either you take the left path or you take the right path. Unless perhaps you're a quantum particle, once you take the left path, you cannot simultaneously take the right path. So one of those paths is the one you take and not the other. One of those propositions is true, the other is false. Another example, if you have the sandwich, you can have either a soup or a salad as a side. If you're given that option at a restaurant, the or is being used exclusively. It's saying you can have one but not the other. You are either going to have the salad or you are going to have the soup. However, there are uses of or in English that are inclusive. And by the way, this applies not only to English, but many other natural languages as well. Many other human languages that were not designed by logicians or mathematicians or computer scientists, computer programmers. These are languages that evolved naturally, and it's common for them to combine the inclusive and the exclusive senses of or. An example of the inclusive or in English, suppose you say, either I'm going to have a hamburger or a hot dog for dinner. Well, suppose you end up eating both. Most often we would say you did not lie or you did not speak falsely. It's okay in that case that you had both, that your statement was still true. If that's how you were interpreting it, then it would be an inclusive use of the word or. So because we're interpreting or inclusively, we cannot directly capture the exclusive meaning of or just with the word or the wedge operator. However, there is a way of interpreting the exclusive or using the notation that we're using. So if we're using only capital letters to represent simple propositions, if we have an exclusive or P or Q, we can write it out as P or Q, but not both P and Q. The key idea is that P or Q is true and not both of them are true. One is true, the other is false. This can be symbolized using logical notation with a wedge, a dot, and a tilde. We also have to introduce parentheses to remove ambiguity, since we have three operators that are joining propositions, one wedge and two dots. So the parentheses notation, it won't come up that often in this critical thinking course, but here we need it to remove ambiguity, to show that the dot in the center is the main operator. The wedge only is linking the P and the first P and the first Q. The second dot is only linking the second P and the second Q. But if we wanted to interpret this notation, it would be saying either P or Q is true, and it's not the case that both P and Q are true. Now let's talk about conditionals in a bit more detail. Conditionals are a very common type of proposition. They occur in many argument forms. So a conditional is a proposition of the form if P then Q, or P horseshoe Q. The if clause is called the antecedent in logic, and the then clause is called the consequent. The antecedent goes before the horseshoe if we're using that notation, and the consequent goes after the horseshoe if we're using that notation. Another type of proposition is called the biconditional. You could think of this as a conjunction of two conditionals. What the biconditional is saying is that if P then Q and if Q then P. So you could think of it as kind of a two-way conditional. It's often symbolized by a triple bar linking two propositions. The biconditional is defined using logical converses. Converses are conditionals in which one has the form if P then Q and the other has the form if Q then P. So they're conditionals in which the antecedent and consequent are reversed. Many logical errors come into play where people confuse a proposition with its logical converse. They have different meanings, they're not equivalent. One could be true and the other could be false. A contrapositive is where you have propositions of the form if P then Q and if not Q then not P. Even though these have a different logical form, unlike the converses, contrapositives are logically equivalent. So here's an example. If you don't eat your meat, then you can't have any pudding. The logical converse of that is if you can't have any pudding, then you don't eat your meat. But those are actually logically distinct propositions. One could be true and the other is false. So for example, maybe the reason why you can't have any pudding is for some other reason that you didn't eat your meat. Maybe you also were a bad boy or something like that. The contrapositives are, however, logically equivalent. So the proposition, if you don't eat your meat, then you can't have any pudding. Its contrapositive is, if you can have pudding, then you do eat your meat. And those are actually saying the same thing, logically speaking.